Welcome to Sri Chaitanya. This is Umasankar. Hi. Actually, in our limits chapter, so far we covered the subject matter into 4 lessons. Of that, lesson 1 is about theory of limits, and lesson 2, 3, 4 are successively the important results and methods for applying limits, for to evaluate limits, etc. things we practiced it. Now my friends, today we are concentrating algebra and standard theorems of the limits. Actually everybody knows about algebra of the limits. That is not a matter here. Even in algebra of the limits also, there are some key points one should practice. And of that, here I am introducing 2 to 3 beautiful and important theorems. And if you are preparing for advanced examination, those theorems and applications of those theorems are very, very important. Actually, in general, nobody will teach those things. But here I am not giving the proofs, but the statements and their applications. Later I will explain the applications. Here, at present, I am explaining the concepts only. Okay, my friends? Now let's see. Now coming to the algebra of the limits. First read the statement properly. Let f be a function defined on a certain interval. This is important. And containing a as an interior point. See, in the previous video I told one important aspect, which is where we are finding limit of the function, the point need not be an element in the domain of the function. It must be the limiting point of the domain of the function. This point I stressed more. But whereas if I am talking about the algebra of the limits, there the terms and conditions are: number 1, the function is defined in what? In a certain interval, whether it is a closed interval or open interval or semi-open or semi-closed. That is immaterial for me. It should be defined in a certain interval. And the point A is an interior point. The point A is an interior point. And for suppose at that point, if limit of the function is f of x is L and the limit of the function g of x is m, where L and m exists in the sense what? They are finite. Then first one is limit extends to a f of x plus g of x. Suppose sum of 2 functions are given to you, then that is nothing but sum of the limits individually. Limit extends to f of x plus limit extends to g of x, which is equal to L plus m. You can write like that. But proofs also very, very important, but for competitive examinations proofs are not necessary. But my suggestion is once after completion of this information, you please ask your corresponding instructors, or if possible, if you are really enjoying my videos, if depends upon the demand and situation, I will explain the proofs also. But only few people will like those kinds of proofs and the depth in the subject. And coming to the second one, limit extends to f of x minus g of x is equal to limit extends to f of x minus limit extends to g of x, that is L minus m. That means difference of limit of difference of 2 functions is difference of the limits of the functions individually, that is L minus m. And coming to the third one, limit extends to f of x into g of x, that is product of the limit of product of 2 functions is equal to product of their individual limits. And similarly, limit of quotient of 2 functions is limit of numerator by limit of denominator, provided m not equal to 0. Everybody tells like this. There is no problem at all. But my question is, what is about the converse? This is important. Actually, so far in our regular examinations and competitive examinations and every test book, they are concentrating only if they give limit of the function f of x and limit of the function g of x, and in general they may exist, and they are asking limit of sum of the functions or difference of the functions or product or quotient, something like that. My question is, there are some functions, though the limit of those functions need not exist, but some of their limit may be exist or may not exist. Similarly, though limit of the individual functions need not exist, but limit of difference of that function will exist at some particular point. Again, the converse of third one is also, though the product, if any of the two limits need not be exist, even then product of the limit must be exist. For that, here I am giving small examples. Suppose something like this. Suppose f of x is equal to 1 when x greater than or equal to 0, minus 1 when x less than or equal to 0, and g of x is equal to minus 1 for x greater than or equal to 0 and 1 for x less than or equal to 0. You take or you consider these two functions. Individually, limit of the function f of x at x is equal to 0 and the limit of the function g of x at x is equal to 0 are not exist. But whereas the sum, what is sum f of x plus g of x? That is nothing but 0 for every x, and it is a constant function, and everywhere limit exists. Even at x is equal to 0 also limit exists. Like that, there are some important counter examples are there. So whenever you are practicing the limits of the theorems or algebra of the functions as theorems, you need to focus on what? Converse of the theorems also. So in that aspect, this is very, very important one. Okay. So I am expecting the questions regarding converse of the theorems. So my suggestion would be, you collect this kind of different examples where the function fails to satisfy the converse. Because in examinations, especially in constructing the examples, they may ask the questions in that angle. Okay. Now coming to my friends, next one is, and this is also limit x tends to f of x whole power g of x is equal to, individually we can separate the limits both for exponent as well as the function in the base, which is L power n. This is possible only if what? The function f of x and g of x has finite limits. If it is in the form of 1 power infinity, or it is in the form of infinity power infinity, or 0 power 0, the story would be different. Here I am talking about what? There are finite numbers and other than 0 also. Okay. And coming to my friends, next k into f of x. Suppose if a function is multiplied by a constant k, then you can bring that constant outside and we can find a limit only to the function, that is k into limit x tends to f of x, that is equal to kn. And this is the comparison limit. This is the comparison limit. So whenever f of x is less than or equal to g of x for all x, then the same will applicable even for the limit also, but converse need not be true. That means limit x tends to f of x less than or equal to g of x. That doesn't mean that f of x less than or equal to g of x. But if f of x less than or equal to g of x, then limit of the functions also maintain the same inequality. The same inequalities we can prove even in the differentiation and integrations and even definite integrations also, they are useful like that. And coming to property number 8, that is the limit of modulus of the function. Limit x tends to a mod f of x, which is equal to mod of limit of the function, that is equal to mod L. Again here I am telling, converse of the theorem need not be true. Converse of the function need not be true. That means though the limit of the modulus function exists, but limit of the original function need not exist. You can verify the previous example which I mentioned in the first slide. Now coming to the ninth property or algebra, limit x tends to a e power f of x is equal to e to the power of limit x tends to f of x, which is equal to e to the power of L. This is these are the 9 important algebra of the functions. And coming to limit x tends to a logarithm of f of x. Yeah, logarithm of f of x. Then you can do one thing, provided here the limit of the function f of x is L and which that number is greater than 0, then what to do? Then you can get a logarithm outside and you can find a limit only to the function which is inside the logarithm. Similarly, limit x tends to f of x, f of g of x. This is a limit of the composite functions. Nowadays, they are concentrating more on this kind of functions. This is very, very composite functions. Composite functions. So limit of the composite functions is very, very important. Here it is implies and implied by, that is necessary and sufficient conditions. See, listen the statement very carefully. Limit x tends to a f of g of x implies and implied by f of limit x tends to a g of x. That is f of m provided f is continuous at x is equal to m. Of course, it is interlinked with what? The chapter continuity, and this is the most important property of continuity of the function of composite functions. Now, the next, my favorite theorem, one of the favorite theorem, which is a squeeze theorem or sandwich theorem. See, actually in previous videos also we discussed about several standard limits to evaluate limit of the function. Sometimes they may fail to find the limit of the functions. At that time, what we do is we apply the comparison. Based upon the comparison between the functions, we can also evaluate the limit of the function. Suppose if you want to find the limit of the function g of x, but it is very difficult to find the limit of the function. But you know limit of the function f of x and the limit of the function h of x and the relation between f, g and h as shown in this one. And moreover, the limit of and extremes of f and g are same. Whenever this kind of situation arises, then the limit of the function which is in between them is also equal to L. That is why it is called what? Sandwich theorem. What is sandwich? Between any two bread slice, if you are putting some other stuff while eating the two bread slices, automatically you can also eat the stuff in between them. The same concept here also we are applying. That means if to find the limit of the function g of x, and if that g of x is lie between two different functions f of x and h of x whose limits are known to you such that they have the same limits, then the function which is in between f of x and g of x exists and is also equal to L. That means equal to limit of the extremes of the functions. This kind of function is called what? Our concept is called what? Sandwich theorem or squeeze theorem. Okay, my friends. And again, here the corollary. Here, mod f of x is less than mod g of x in certain neighborhood of A. What is NBD? Neighborhood of A. And moreover, limit of this g of x is 0, then limit of x is also 0. And problems were repeated on this particular concept several times in JEE advanced examination. Please don't neglect and collect as usual the best and beautiful examples just like I mentioned in the previous slide. Okay, this is also one of the important, and this is also one way corollary of the sandwich theorem, I can say. So if you know the limit of mod g of x and which is 0, then limit of f of x is also 0, and this property itself as a bit they may ask or we can expect in any of the competitive examinations. So far they have not directly asked in mains examination. At any of the mains examination we can expect the same results, the same things in one of the mains examination also, because already they asked in advanced examinations. Now coming to my friends, neighborhood property. Again, problems were repeated in JEE advanced examination. Actually, nobody knows this property. Even in your regular textbooks also, they never concentrate on this kind of property. This is very, very useful property. Listen the statement very carefully and read it very properly. If limit of the function f of x is L, then there exists some neighborhood of A. At every point of f of x will have the same sign as that of L. What does it mean? Suppose if a function is, if you take any function, suppose see this is my function and this is my origin. Suppose this is my function y equal to f of x. This I have taken the function like this. This is y equal to x square. This is my origin. You take some neighborhood and the limit of this function, if this is my function f of x is equal to x square. Then limit extends to 0, f of x is equal to limit extends to 0, x square, which is equal to 0. No problem, no issue at all. Here my a is 0. So in the neighborhood of 0, how many neighborhood will exist? Infinitely many neighborhoods of 0 will exist. How? That already I told. What is the neighborhood? Epsilon neighborhood of a point A, I told. Because suppose if epsilon greater than 0 is any positive real number, and a is any real number, then open interval a minus epsilon comma a plus epsilon is called what? Epsilon neighborhood of the point A. And epsilon greater than 0 is what? Smallest positive quantity, however small it may be. Okay, so based upon epsilon we may get infinitely many number of neighborhoods. That is the power of epsilon. So just like you take any neighborhood of that 0, And observe the sign of f of x. Observe the sign of f of x. The sign of f of x and the values, the sign of the limit both are same. That means if f of x is positive, then sign of L is also positive. If f of x is negative, then sign of L is also negative. This kind of property is called what? Neighborhood property. Minimum 2 to 3 times questions were repeated based on this application. Now the same corollary here I have mentioned with the same example, f of x is equal to x square. See, listen, limit x tends to f of x is equal to L. Suppose f of x is positive at every x. See, this I told. Suppose if I have taken my function like this, and this is origin, suppose this is my neighborhood. Actually neighborhood is not in that length. Okay, for our convenience only I have taken. These are all are what? F of x. And these are all are what? F of x. F of x is what here? This is greater than 0. So here, see, if f of x greater than 0 for every x, then in a certain neighborhood of a, then L is also not non-negative. And if f of x is less than 0 for every x, in a certain neighborhood of a, then L is also not positive. Okay, na? And if L is equal to 0, that means if f of x is equal to 0, automatically L is also 0. The same thing here we mentioned, and this property is called what? A neighborhood property. Again, please practice the different varieties of the examples and counter examples to support this particular model. With some theoretical questions also, I will explain this properly after this lesson. Now coming to another important one, Cauchy's criterion for existence of limit of the function. So far we have practiced so many theorems and existence of theorems, and when can we say limit of the function exists? I simply limit x tends to a, f of x is equal to L exists. When can we say both left hand limit x tends to a minus f of x exists, and right hand limit x tends to a plus f of x exists, and are equal, limit x tends to a minus f of x is equal to limit x tends to a plus f of x, and is equal to L, then only we can say that the limit of the function is L. This is what existence of limit of a function at a point. Yeah, the same thing Cauchy has given in another direction, the same concept. Read that statement properly. The necessary and sufficient condition that f of x may tend to a definite limit L as x tends to a. This is necessary and sufficient, and that means implies and implied, both the ways it applicable. You take any epsilon greater than 0, however small it may be, automatically there exists a delta greater than 0 which depends upon epsilon, such that mod of f of x1 minus f of x2 is less than epsilon for every x1 comma x2, which satisfies 0 less than mod x1 minus a less than delta and 0 less than mod x2 minus a less than delta. What does it mean? Actually, x1 is in some delta neighborhood of a. That means this is a minus epsilon, a minus delta comma a plus delta. So suppose this is a and this is a minus delta and this is a plus delta. That means you take any two values in this particular neighborhood x1 and x2. There are not any exterior points of that deleted delta neighborhood of a. They are inside the any 2 points you take. At that point you take the difference of the functional value. I can call this as oscillation of the function. I can call this is what? Oscillation of the function. So for any two different values in the neighborhood, whenever the oscillation of the function is also less than epsilon, then we can say that the L is limit of that function f of x as x tends to a. This is called Cauchy's criterion of the function. Okay, and of course very difficult and typical problems one can expect from this as an application. For you just concentrate on or imagine the nature of the function and what is the oscillation and how it occurs, because how epsilon and delta will exist, and what are the roles of epsilon and delta, and what are x1 and x2, existence of that x1 and x2 is very, very important. Okay, so you just imagine that one. So the same thing is nothing but, as we said, limit x tends to a f of x is equal to L. What we said, limit x tends to f of x is equal to L analytically. For epsilon greater than 0, there exists a delta greater than 0, which depends upon epsilon, such that mod f of x minus L is less than epsilon whenever mod x minus A less than delta for every x. Isn't it? That means you take any epsilon, there exists a delta which depends upon the epsilon, such that whenever mod x minus A is less than delta, then the distance between f of x and L is also less than epsilon. Then only that real number L is called what? Limit of the function as x tends to A. Symbolically, we represent that as what? Limit x tends to A, f of x is equal to L. Of course, my friends, majority of the people may not understand this properly. Don't worry, but my suggestion would be you just practice the terminology. Don't worry about the exactness and etc. etc. But if you are thorough with the terms and the terminology of and if your imagination, if you are improving the imagination why the oscillation is less than epsilon with the practical examples, then only you will enjoy the purpose of the theorem. Now this is about Cauchy's criterion for existence of limit of the function. And coming to here, I am giving another beautiful definition. This is also Cauchy's theorem or Haynes theorem, I can say. Here I am giving the two definitions. Both the definitions are equivalent. That means one implies definition 1 implies definition 2. Definition 2 implies definition 1. Actually, first definition is familiar for you because just now also we discussed it. What is that? Limit x tends to f of x is equal to L if what? For any epsilon greater than 0, there exists a delta greater than 0 such that mod f of x minus L less than epsilon for all x less x, for all x belongs to 0 less than mod x minus L less than delta. This is original definition, analytical definition. The same definition again we can also treat with sequences. See, before that I would like to introduce limit of the sequence. Suppose limit x tends to limit n tends to infinity xn is equal to L. What does it mean? That means this is a sequence xn. Sequence xn means it contains terms x1 comma x2 comma x3 comma and so on. For example, my sequence xn is equal to 1 by n, where n is a natural number. This is my sequence. That means my sequence is what? 1 comma 1 by 2 comma 1 by 3 comma 1 by 4 comma like that. This is called a sequence. How to find the limit of this sequence? That is limit n tends to infinity. Why here I am using n tends to infinity? Because every sequence contains infinitely many terms. So here I am applying n tends to infinity means x1, x2, x3, x4, x5. What is the trend? What is the trend in the terms of the sequence? Where they are going and reaching, approaching, that number is nothing but limit. This how can we say? The same thing we can define like this. Given epsilon greater than 0, however small it may be, there exists a positive integer m. There exists a positive integer m. Be careful. In sequences I am mentioning a positive integer m. M belongs to n, such that modulus of xn minus L less than epsilon for every n greater than or equal to m. See how beautifully it is defined. That means, suppose these are the terms of the sequence. Say x1, x2. These are, suppose this is some L, neighborhood of L. This is L. This is my sorry. These are the terms of the sequence. 1, 2, 3 I am taking. See, on the real line I am taking like this. This is 0, 1, 2, 3, 4 and so on, n and so on, n plus 1 and so on, n plus 2, something like that. and this is my L, this is my L minus epsilon and L plus epsilon. See, this is my L. Suppose this is the function. When can I say what is the limit of this sequence f of xn? That is the limit n tends to infinity 1 by n is what? 0. The concept of limit as graphically or geometrically I can give like this. For epsilon greater than 0, there exists a positive integer m depends upon epsilon such that modulus of xn minus L less than epsilon for every n greater than or equal to m. That means for x is equal to 1, that means the corresponding first term is x1. That x1 need not be in the neighborhood. It may belongs to in the neighborhood or may not. Suppose for x is equal to, this is x2. x2 again need not be the term in the neighborhood. This may happen up to some extent. That extent is called m. After that, if for every n greater than or equal to m, if every term xm, xm plus 1, xm plus 2, xm plus 3, all are lie in between L minus epsilon comma L plus epsilon, then we can say that number L is a limit of the sequence. The same thing here we are giving in another way. Limit of the function f of x as x tends to a is equal to L when sequence of f of xn is equal to L, provided there exists a sequence xn in the neighborhood of a where it converges to a. Converge means limit is exists. If limit of the sequence is finite, then we can say that the sequence is converging to L. That is the terminology in sequence and series we can use. So sequence xn has limit L means what? Sequence xn converging to L. Symbolically we can represent like this: sequence xn converges to L. But symbolically we can also write this as limit n tends to infinity xn is equal to L. Both are same. In sequence language we represent the converging of the sequence like this. In limit form we can represent like this. So what is the definition to limit of the function f of x is equal to L whenever sequence of f of xn converging to L. As n tends to infinity, for all sequence xn in the neighborhood of a where that sequence xn converging to a. Here they are looking like two different statements for existence of limit of the function, but both the statements or both the definitions are equivalent. That means we can prove definition 1 implies definition 2 and definition 2 implies definition 1. With the help of this definition, we can prove a certain peculiar problems, and those problems can be solved only with this help of this particular concept. This definition is called what? Cauchy and Haynes definition of the limit. I will give in next lesson two conceptual beautiful problems or applications of this particular Haynes definition. You will enjoy. This is another beautiful theorem on definitions of limit. So my friends, 15 theorems, algebra, and of that neighborhood property, Cauchy's criterion and Haynes definitions, they are another advanced concepts in the theory and theorems of the limits. Now my friends, this is about lesson number 5. If you like this, you please share my channel and subscribe this, and we will meet the standard expansions for finding the limits very soon in lesson number 6. And this kind of information always we have been providing to our Sri Chaitanya students, and you better utilize this opportunity. Thank you.